Hi, and welcome to the first lesson in the Physics Atomic Structure topic. So this is the fourth topic in the Physics GCSE. My name is Mrs. McGee and I'm one of the Science Directors. And today in this lesson we are going to recap atoms and isotopes. Now you might remember some of this from your chemistry lessons, but it is also very important in this unit. So we're going to start with our starter, and what I'd like you to do is just see what you can recall about atoms. So I'd like you to describe what you can remember about the structure of an atom. What particles is it made of? Where is it that they're located? You might want to draw a diagram. If you remember the names, you might label that diagram, but just take 2 minutes to write down or draw anything that you can remember about atoms from what you've learnt before. Off you go. So in this first lesson, we are going to first describe the structure of an atom, and we're going to practice drawing some atoms and look at what information we can get from the periodic table about atoms. And then in the second part of the lesson, we're going to explain what isotopes are. So let's see what we remember about atoms. So you should remember that atoms are incredibly small. Okay, so if we imagine that if we think of atoms as a spherical object, okay, so we tend to draw them as spherical objects. Now the radius of an atom is approximately 0.0000000001 meters wide. Okay, so that is 1 times 10 to the power of minus 10 meters is the approximate radius of an atom. Okay, if you compare it to a football, an atom is 3 billion times smaller than a football. Okay, so if we increased an atom by 3 billion times, then you'd be looking at something the size of a football. So that's how incredibly small atoms are. So what else do we need to remember about atoms? Well, we need to remember that atoms are made of protons, neutrons, and electrons, and that the protons and neutrons are found in the nucleus, and that the electrons are found in shells around the nucleus. So hopefully you remembered some of that in your starter activity. We're going to now quickly recap the mass and charge of these different subatomic particles. So I'd like you to just draw this table here, just really quick. The three particles are protons, neutrons, electrons, and then we'll look at the relative mass and the charge. Pause the video quickly if you need time to sketch this out. Okay, So again, this is a recap from things that we've done before in chemistry. So every part of the atom has its own relative charge. And you will hopefully remember that electrons have a negative charge, protons have a positive charge, whereas neutrons have no charge at all. They are neutral. Now, the way that I like to remember this is if you look at the word neutral, that is very similar to the beginning of the word neutron. Okay, so neutrons are neutral. And then positive starts with a P, as does proton. So protons, P, positive, P. So protons are positive. So neutrons, neutral, protons, positive, and then electrons is just what's left over. Okay, so the electrons are negative. So let's now look at the mass of each of these parts of the atom. So protons and neutrons both have a mass of 1. Okay, now we don't give a unit for the mass of protons and neutrons because they are so incredibly small that trying to compare them to things that we might measure in meters or in centimeters would just make the numbers incredibly difficult to work with. So we just say that a proton has a mass of 1 and a neutron has a mass of 1. Okay, so protons and neutrons both have the same mass. Yeah, so relative to each other, they are the same size. Now, compared to the protons and the neutrons, the mass of electrons is 1 divided by 1,840. This is an incredibly small number. So what we can say as well is that the mass of an electron is almost 0. You can't say that it is 0 because that would mean electrons have no mass at all, which isn't correct. Okay, but their mass is almost 0. So that's what you can say. So protons and neutrons have a relative mass of 1, so they have the same mass as each other, whereas electrons have a mass of almost 0. So you should have been filling out your table whilst we went through that. So what your table should look like is that your proton has a relative mass of 1 and a positive charge. So you can say a charge of +1. Your neutron also has a mass of 1, but it has no charge. So it has 0 charge, and we call this neutral as well. And then your electron has a relative mass of almost 0, and it has a negative charge or -1. Okay? So let's now quickly recap how we would draw the electrons in an atom. So here's the example of argon, and you can see that in the nucleus, argon has got 18 protons and 22 neutrons. Now, when we draw atoms, we don't tend to draw the protons and neutrons in the nucleus because you get to the point where there are just too many of them and it would just be a waste of time. But we do draw the electrons in shells quite often, and you need to remember that the first shell in an atom can hold a maximum of 2 electrons. So the first shell is this one here. Okay, so it's the inside shell. So that's your first shell. Then the second shell can hold a maximum of 8 electrons. So your second shell is this one here, is your second shell, and that can hold a maximum of 8 electrons. And then your third shell here can also hold a maximum of 8 electrons. Okay, now in the case of argon, all 3 of these shells are full. Okay, so we've got 2, 8, 8. But obviously with different atoms that have different number of electrons, not all the shells will necessarily be full, but the inner shells are always full. Okay, so you always have to fill the first shell before moving to the second one when you're drawing an atom, and then you fill the second shell with up to 8 electrons before you move on to the next shell. Okay, so it's never the inside shells that are not full. It's always the outer shell that might not be full with different atoms. Okay, so if I give you another example here to explain what I mean, so let's look at carbon. So carbon has 6 electrons in it, so I'm going to just put a dot for the nucleus, and I'm going to draw my first shell. and I'm going to do 2 electrons on that first shell. Now we typically use an X to draw electrons. So that first shell is now full, but I have only drawn 2 electrons, but I need 6 in total for carbon. So I'm going to draw another 4. So I need to draw a second shell, and this time I'm going to space my electrons out, and I tend to draw them north, east, south, west. So top, right, bottom, left, going round that shell. So there is my carbon drawn now with 6 electrons, 2 in the first shell and 4 in the second shell. And I can write this electronic configuration like this. So 2 electrons in my first shell and then 4 electrons in my second shell. Okay, I can show you another example. Get rid of that one. So let's pick another example. For example, let's look at sodium. Okay, so sodium has got 11 electrons in the atom. So I'm going to do a dot for my nucleus. I'm going to draw my first shell with 2 electrons on it. But I need another 7 to get to 11 electrons. So I'm going to draw my second shell. Sorry, I need another 9, not another 7. My second shell. So I'm going to draw 1 electron at the top, 1 on the right, 1 at the bottom, then 1 on the left. And I can now fit more electrons in that second shell. So I'm going to now pair them up. We tend to pair electrons up like this. So top, right, bottom, and left again. So far I have drawn 2 electrons on the first shell, 8 electrons on the second shell. That still doesn't add up to 11. I need 1 more electron. So I'm going to draw a third shell. And I'm going to add my 11th electron on that third shell. So I've added 1 electron on that outside shell. So 2 electrons on my first shell, 8 electrons on my second shell, 1 electron on my third shell, which adds up to my total of 11 electrons, which is what I said I needed at the start. So the electronic configuration is the way in which electrons are arranged in an atom of a particular element. Okay, and these shells that we have been drawing, we can also call energy levels or energy shells. So we have the inner shell is our lowest energy level, and then as you add more shells, you are going up the energy levels. Okay, so electrons in the first shell are at a lower energy level, and then electrons in the next shell will be at a higher energy level. So when atoms absorb electromagnetic energy, their electrons can move to higher energy levels. So this electron here has absorbed some energy, so therefore it moves to a higher energy level. Okay, and the reverse is also true. When the electrons lose energy, for example, by emitting light, they can return back to lower energy levels. Okay, now the amount of energy needed to move from one energy level to the next is the same regardless of whether the electrons are moving up or down the energy levels. So to move from the first shell to the second shell, the electron has to absorb a certain amount of energy. But to move back from the second shell to the first cell, it releases that same amount of energy that it absorbed before. So if we now look at the information that's given to us in the periodic table, earlier on I drew some examples of atoms and I just said how many electrons they had before I drew them. Now the reason why I knew how many electrons they had is because I was looking at a periodic table that's next to me. So our periodic table gives us really important information about elements. Every element in the periodic table will have 2 numbers. This first one here, which is the smaller number, is called the atomic number. And the atomic number tells you how many protons there are in the atom. Okay, so it's the proton number is another name for it. And then the top number here tells you the relative atomic mass of the atom. Okay, so that is how heavy the atom is. Now, if you remember from earlier on in the lesson, we said that protons have a mass of 1, and we said that neutrons also have a mass of 1, and we said that electrons have a mass of almost 0. Okay, so when we're looking at the overall mass of an atom, we can ignore the mass of electrons. They're negligible, okay? They're so small that we can just discount them entirely. So when we're looking at the mass of an overall atom, really what we're looking at is the mass of the protons and neutrons added together. Okay, so we're actually looking at how many protons and neutrons there are. So this relative atomic mass actually gives us the number of protons plus neutrons that there are inside the nucleus of the atom. Okay, so in this example here for lithium, the mass number is 7. And if you look at the diagram, you can see that lithium has 3 protons and 4 neutrons. Well, if you add those together, that gives you a mass of 7, which is the relative atomic mass that's given here for lithium. Okay, so we can use this information to work out how many neutrons might be in an atom. So I know from the periodic table information that lithium has got 3 protons here. I know from the periodic table that my mass is 7, therefore lithium must have 4 neutrons, okay, because protons and neutrons added together gives me my overall mass. Now, we're going to look at some more examples of this in a minute. Now, the last bit of information that we need to know is that the number of electrons is the same as the number of protons. So in this example, where we have 3 protons, that means that lithium will also have 3 electrons, okay, which is what you can see here in the diagram, 3 electrons drawn. So let's have a look at some more examples now from the periodic table. So if we look at beryllium to start with, you can see here that the atomic number for beryllium is 4. So that tells you that beryllium has got 4 protons. Now the mass number for beryllium is 9. So we can work out from this how many neutrons there are. So the mass number tells us that there are 9 protons and neutrons added together. So if there are already 4 protons, that means that we must have 5 neutrons. Okay, and then the number of electrons, remember, is the same as the number of protons, so that is 4 electrons for beryllium. So in our nucleus, we've got our protons and our neutrons, and then we've got electrons in the shell. Let's pick another example now from our periodic table. So if we now look at fluorine, fluorine has got an atomic number of 9. That means that we have got 9 protons. It has got a mass number of 19. So our neutrons, which are in the nucleus with our protons, if you add them together, you get a mass number of 19, which means that we must have 19 take away 9 equals 10 neutrons. And then our number of electrons is the same as our number of protons, which is 9. And let's look at a third example just to really reinforce this. So if we look at hydrogen now, hydrogen has got an atomic number of 1, so that tells us that there is 1 proton. The mass number of hydrogen is also 1, so in our nucleus we have got protons and neutrons adding up to a mass number of 1. But if we already have 1 proton, that means if we take the difference, we have got no neutrons in this atom of hydrogen. Okay, so we have 1 proton, we have 0 neutrons. And then our number of electrons is the same as our number of protons. So that is 1 here for hydrogen. Okay, so what I'd like you to do now is to do this yourselves for carbon, sodium, helium, and phosphorus. I'm going to give you 2 minutes to do this. So for each of them, I'd like you to work out how many protons there are, how many neutrons, and how many electrons. You've got 2 minutes, off you go. So let's see how you got on. Here are the answers. I'm going to give you a minute to check them against what you have written. Okay, if you need a bit more time, then just pause the video and press play again when you're ready to move on. Okay, so you should now be feeling more confident with working out numbers of protons, neutrons, and electrons from the mass number and atomic number that you find on periodic tables for different elements. So as a quick recap, before we look at what isotopes are, I'm going to give you 2 minutes to copy these sentences and complete the gaps with the keywords that you think will best fit. You've got 2 minutes, off you go. Okay, 2 minutes is up, so let's see how you did. So first question, A is the atomic mass or the mass number, and Z is the atomic number. B, the mass number is equal to the number of protons and neutrons added together. And C, the atomic number is the number of protons. D, this is also equal to the number of electrons. So well done if you got those right. So in the first part of this lesson, we looked at what the structure of an atom is, how to describe it, and how you can work out numbers of protons, neutrons, and electrons. We're now going to look at what isotopes are. So let's look at these two atoms of carbon using what we have already learnt in this lesson. So if we look at this left-hand carbon here, you can see that the atomic number is 6, so that tells us that it has got 6 protons, and it will also have 6 electrons because they're the same number. But if you look at the mass number is 12, so this tells us that the number of neutrons, remember you do the difference between mass number and atomic numbers, it's 12 minus 6, so that is 6. So this carbon has got 6 neutrons. If we look at this right-hand carbon atom now, so the atomic number is still 6. So the number of protons is still 6 and it will still have 6 electrons. But this time the mass number is 13. Okay, so it's one more than the 12, which was the mass number of the carbon on the left-hand side. So this tells us that our number of neutrons is going to be different. And in this case, the number of neutrons is 13 take away 6, which is 7. So both of these atoms are still carbon because they still have 6 protons, and the number of protons is what determines which element it is. Okay, so they still have the same number of protons, they still have the same atomic number, so they're both still carbon atoms, but they have different numbers of neutrons. The left-hand carbon has got 6 neutrons, the right-hand carbon has got 7 neutrons, so they have a different mass number. So they're different versions of a carbon atom. This is what we call isotopes. Okay, so these two atoms of carbon are both carbon, but they're different versions. They are isotopes of carbon. So an isotope is two atoms, so an isotope is two atoms which have the same atomic number, so the same number of protons, but they have a different mass number, and this means that the number of neutrons is different. If you didn't remember those definitions, then just pause the video now and make a note of that in your notebooks. So carbon exists as 3 isotopes, carbon-12, carbon-13 and carbon-14. And these numbers, 12, 13 and 14, refer to the mass number, the atomic mass of carbon. So here's the first one, carbon-12, which has got 6 protons, 6 neutrons and 6 electrons. Carbon-13 still has 6 protons because it's still carbon, but this time it has 7 neutrons because it has one more for its mass number, and it still has 6 electrons. And then carbon-14 still has 6 protons, but this time it has 8 neutrons and it still has 6 electrons. There are different elements that also have isotopes. So hydrogen is another element that has different isotopes. So hydrogen 1 makes up the vast majority of naturally occurring elements, but there are 2 other isotopes. So if we look at hydrogen 1 first, it has 1 proton, no neutrons and 1 electron. And we drew this one earlier on in the lesson. But you can also get deuterium, which is another type of hydrogen. So it still has 1 proton, as all hydrogen atoms do, but this time it has 1 neutron. And then you can also get tritium, which is a third isotope of hydrogen, still has 1 proton because all hydrogen atoms have 1 proton, but this time tritium has 2 neutrons. And so you can see that the mass number for tritium is 3, and that's because it has these extra 2 neutrons, which you add to the 1 proton to give you that mass number. Now here's another example for oxygen. So almost all naturally occurring oxygen is oxygen 16, so it has a mass number of 16, but about 0.2% is oxygen 18. So oxygen 18 has a mass number of 18, whereas our most common form of oxygen has a mass number of 16, so oxygen 18 must have 2 more neutrons than oxygen 16 does. So let's have a look. So oxygen 16 will have 8 protons, 8 neutrons, and 8 electrons. Okay, so just to recap, the 8 protons, we know that because the atomic number is 8. And then we know that it has 8 neutrons because you take the mass number and you take away the atomic number. So 16 take away 8. Let's write that again. 16 take away 8, and that leaves you with 8 neutrons, and then it has 8 electrons. So what do you think it will be for oxygen 18? So for oxygen 18, we're going to have still 8 protons because the atomic number is still 8. Okay, so that doesn't change. But this time the mass number is 18, so we can work that out. 18 take away 8 gives us these 10 neutrons here. So oxygen 18 has 2 more neutrons than oxygen 16 did, and it still has 8 electrons. So what I'd like you to do now is try and write down your own definition for isotopes. So use the keywords that I have given you there, so element, atom, protons, and neutrons. And then I'd like you to calculate the number of protons, neutrons, and electrons for these 2 chlorine isotopes. So you've got chlorine 35 on the left and then chlorine 37 on the right. And I'm going to give you 3 minutes to answer these 2 questions. Off you go. So let's see how you did there then. So for the definition of an isotope, you might have written something like, isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. And then for your calculation of the protons, neutrons, and electrons for the two chlorine isotopes, so chlorine 35 has got 17 protons, 18 neutrons, and 17 electrons, whereas chlorine 37 has got 17 protons still, 20 neutrons this time, and still 17 electrons. So correct what you've done, or give yourselves a tick if you got that right. So here are the two isotopes of chlorine, just to look at again. So about 75% of the naturally occurring chlorine is chlorine 35, so this one here on the left, whereas 25% of chlorine is chlorine 37, so this example on the right. So that's the end of our lesson. So well done. You should now be really confident with describing the structure of the atom and explaining what isotopes are. On this last slide then are just some summary notes if you feel that you have missed any of this and would like to add it to your notes, and I will see you in our next lesson.